it's not Susana Frases. But I would like to thank Professor Mary Van Hill today that will be here presenting his work and will very soon be presented by Professor Vanderlei Souza. Professor Mary, thank you very much for taking your time to be here. And I would like to thank you on behalf of our graduate school of biology at the Biophysics Institute of our university. So Professor Vanderlei Souza, whenever you have some time, you can just move ahead and please present us Professor Mary Van Hill.
Okay, Fabio. Good morning, everyone. I know that there are people. Afternoons, not good morning. It's a great pleasure for me to introduce Professor Marin Van Hill. It's a person that I know very well, his basic works, but I never met him. But during a congress in Durban, South Africa, International Congress of Microscopy, by accident we met, and then we established a good friendship. Probably he'll talk something about this. But Marin did his basic formation at the University of Delft and the University of Groningen in Italy, where he developed, or he made his PhD in biochemistry and biophysics, published his first papers. Then he was investigator at the Max Planck Fritz Haber Institute in Berlin. That's a very well-known institution. And then he moved to the Imperial College of London, where he founded and was the first director of the Centre for Structural Biology of the Imperial College of London, where he made many experiments and published many papers. He's also Van Arkel West Professor at the University of Leiden and investigator at the what we call ELINANO, the National Laboratório of Nanotecnologia, that integrates the Centro Nacional de Pesquisas em Energia e Materiais-CPEM, that is the biggest scientific complex in Brazil. We will have the opportunity in 2 or 3 weeks to hear about CPEM in a lecture like this one, not part of this program, but Professor Rogério Cerqueira Leite will tell us about the history, present situation, and the perspectives of the CPEM. Martin has published many papers, most of them very well cited by the scientific communities, with almost around 15,000 citations. That is the number I have. This, of course, changes every day, with a and cited throughout the world. He is pioneer in the technique, in the single particle analysis that allowed electron microscope to be used as an important instrument or important technology to determine the three-dimensional structure of proteins and of protein complex. Those proteins that cannot be crystallized to go to X-ray diffractions, or larger proteins, really the single particle analysis is the best method we have today to determine the three-dimensional structures. Due to this work, he was, I would say that he should get the Nobel Prize. This is something that I never had the opportunity to tell him Marin, but really not only me, but most of the international scientific community working electron microscopy thinking that a few years ago, when the Nobel Prize was given to the people working in three-dimensional reconstruction, free frozen samples, electron microscopy, you should be among them. But there is some role that only three can get the prize, but your work is really considered, and for me, you got the Nobel Prize in electron microscopy. He made the first three-dimensional reconstruction of a human chromosome using electron microscopy. This is many years ago. And more recently, he is working several protein complexes like plant photosystems 1 and 2, skeletal muscle calcium release channel, hemoglobin, bacteriophages, hemocyanins, and so on. So they are always doing something new and something really important in the area of electron microscopy of proteins. So that is really a pleasure to have you.
For the very friendly introduction. I am a bit quiet today. Maybe, I don't know, I have to wake up a bit. I'm very happy that I told you, Vanderlei, that we had a real issue with a patent application and that needed to be submitted before I could speak about the issues here, new issues at least that we're looking at the moment. I can now tell you that here we have I don't know if I'm visible here, but we have here the 128 pages of patent application that went out yesterday evening. And so I am completely free to speak about everything because my patent lawyer didn't allow us to talk about these things. So that was it's been continuous work for month and month, and so I'm maybe a little bit tired today. But okay, so I hope I can still get a very coherent story for you together, in spite of all the continuous activities that we've had over the last few months during the pandemic. The pandemic has, of course, a certain influence on everything. I mean, you can see the length of my white hair has grown. I'm almost as much hair now as I had when I was a hippie and a teenager. But so be it. It's better to have long hair than to have COVID-19. So we've been locked up here for the last 5 months, and I now have installed a home office that is separate from the living room, so we can actually talk and give lectures without disturbing my wife. So, okay, now let me just go to the lecture here, and today is the 3rd of September, Information in Glycosylation. I've been listening to a number of the lectures here in this series, and I was very impressed. And but I've also noticed that the focus was a little bit on. I will be speaking a little bit more on physics than on biology, but thinking about fundamental principles in physics and how they influence biology. That's I think a very challenging a topic for biophysics. 75 years of the biophysics in the Chagas Institute, and so biology is a challenge, and it's very messy. You can see here all these messy plants in the background. I mean, so biology is a very noisy mess, and you need powerful statistics to make sense of these very, very, very noisy data. And so very, very noisy data, significant implies that we're talking about very low signal-to-noise ratio data. And so we're going to have a long story going from physics to biology, and and even the SARS virus. But just to give you the overview over the whole story, just to begin from the beginning to the end, I have just made 2 slides abstract, and everything else in between. So if you already have an idea of what the whole story is going to be. So here, the beginning is the paradigms that I'm going to talk about in physics, and that's here, a physics paradigm. I'm going to talk a lot about signal-to-noise ratio. That's the power of a signal over the power of the noise. It's something when you go to university in electrical engineering or in physics, or you get that just the first thing you hear in your first year. Yes, you need to have a good signal-to-noise ratio. Okay, but so this is a concept. We are trying to trace this concept back to where its origin is. Its origin is about 120 years ago or so, at the turn of the century, 48, to define information. So here we see the information. If your information here is if the signal-to-noise ratio, that's the same signal-to-noise ratio as there. If it goes down to a very small number, then this goes to the value 0. And if it goes to a very large number, you get a lot of information. That's the idea. So this is the physics paradigm where we start off. And then we're going to end today with the sugary biological hide-and-seek wars of the SARS-CoV-2 virus. And I'll just give you a little idea of what's happening here. We have a hard core in dark blue of this trimer, of the S protein, and on the outside you see these things sticking out. Those are N-glycosylations, and here at the end of these tips here is also full of glycosylations. And inside you can see that inside this is the protein. The texture on the outside of the glycosylation is different from the texture on the inside. So so that's the it's starting again. This is not the idea here. Oops. 1 second. I have it the right spot. And let's now go to the this was the abstract, and I'll go to the body of the story. So here, as I said, biology is a very noisy mess, and we have to have very good statistics to understand these very low signal-to-noise ratio data. And talking about very good statistics, I have to also immediately warn you of sloppy statistics, bad statistics that people use every day to claim things that are wrong or incorrect. And I'll give you a number of examples of that it's almost like don't trust any statistics that you didn't falsify yourself, which is a famous proverb from the earliest 20th century. But so here, beware of sloppy statistics. What happens if you have too much of sloppy statistics? Well, that has some very nasty consequences. And here's a very clear case of a sloppy statistics. We here have on the left-hand side the inauguration of President Obama in 2009, and you see it's absolutely full of people. But of course, here there are many more people. This was the inauguration of forget his name in 2017, and so we're all very, very anxious to so on. And with this warning here, let me tell you what I think is sloppy statistics. Here's a joke that I picked up from that somebody from the internet. Somebody sent me, and here we have a picture from the Second World War. We have here this is the statement of this. My granddad was a World War II veteran. In just one day during the Battle of Britain, he destroyed 8 German aircraft, killing 32 Nazi aviators. Easily the worst mechanic the Luftwaffe ever had. And so that's a social joke, of course. Yes, I mean, a bad mechanic will kill the plane. But if you recognize these planes, this is the bomber, the Heinkel 111 bomber that the Germans used to bomb England and other places, of course, during World War II. But it's not just a joke, because here we have the concentration camp north of Berlin. This is the Sachsenhausen Oranienburg concentration camp. And unfortunately, my father was imprisoned there after the German invasion into Holland. He was taken a prisoner as a young student. And he was forced to build these planes here, these Heinkel 111. And what he told me is that all you could do to sabotage the production and not be executed is to play with the statistical tolerances. So this is what he was telling me. Play with the statistics. Statistics is very serious. So you have to understand your statistics so that you don't get killed. Luckily, the World War II didn't came to an end at one point. And so leaving all the misery of the broken Europe behind, my parents then decided to go south and cross the equator at the end of 1949, and crossing the equator and on this ship here, and on this boat was today's speaker. And it so happens then that I spent the first 10 years of my life in Brazil, and went to school here, and so actually it's such an honor to talk to Rio de Janeiro. I wish I was there, Wanderlei. This is really we could have a beer after the talk, because this is just maybe not so clear yet, but I mean, Rio de Janeiro is for me a very important place. And the first time I arrived in Rio de Janeiro was in 1949, and this was the view from the boat. And I gave a lecture in Rio de Janeiro very recently, or last year, just before in August. And I remember this building is still there. This is the Central de Brazil. This building is still there, and they're restoring these buildings here on the port where the ships, the immigrants landed. And now all full of high risers. Actually had a meeting there. And in microscopy, and it so happened then that was educated in the Brazilian system, and coming back from school here in the second grade, there are 2 lines here, second grade at the Nestle plant that my father was the director of, and but what was very important for me was if you go behind the house and look to the left here, you see this here. Oops. You see this here, this on the other side of the street, you had the Cerâmica Porto Ferreira, and Dr. Nicolau Forjas was the director of that, and the steam train would come by twice a day or 4 times a day, I forget. But, so that's a famous ceramics, and I was a bit of a friend with his son, Nicolauzinho. And Nicolauzinho was a few years older than I, and for his birthday, he got an optical kit like this here. This is a modern version of that. And since he was a few years older and I wanted to put my fingers on that, he said, "No toca, no mexe." So he didn't allow me to play with it. So anyway, that was my first frustration in optics. But nevertheless, my second experiments were like in the garden, and doing simple things like doing the Fourier transform of plane wave hitting the lens here, and then putting a focus onto a leaf and burning the leaf. So these are the first Fourier optics for beginners experiments. And here is the Fourier optics for beginners. You have plane waves coming into passing through the front focal plane of the system, then through the lens, and focusing in a single point. So parallel waves in illumination. I think I have two slides over each other. Yeah. So parallel waves illuminating the object from the left are focused into a single back focal plane. So we have a constant wave hitting here the front focal plane, and this focuses into a single point, and that is the concept is transferred into a delta function, a very sharp peak. That's the Fourier transform of a constant. So, and then also, if you have like two of these focal plane, which is then focused into a single point. So you have a point into a point. This is an imaging system. Okay, this is going far. My father didn't stay with Nestle until the very last year. The very last year we were into he was into Fokker airplanes. This here is one of our trips up and down between Brazil and the Netherlands. And this was a modern plane of those days, a super Constellation, a classical plane for international flights made in the first world and traveling between the first world and the third world that people think Brazil is. And in the last year, 59, my father was working for Fokker. And here we see my father selling Fokker airplanes. This is a Fokker Friendship F-27 to Jânio Quadros here, who was the governor of São Paulo at the time. I still remember this model here. This I used to play with it. I loved it, and my father didn't like it because he needed it for presentations. But it was aluminum, and it was cast aluminum. It was heavy and very nice. And anyway, so this was also first world plane being sold to Brazil, and it became a success in Brazil. And but things changed, and in more recent years, things are different. Last 2 years or before the last few years before coming to Brazil, I was commuting between London and where we lived and Amsterdam or Leiden University where I was working. And so when I would take a British Airways flight, so there was a commuting over the channel and flying from London to Amsterdam, could have this plane here, which was or on the way back after a long week of work, a KLM plane flying from Amsterdam to London. And in both cases, we're talking an Embraer 190. And so I always show this to my Brazilian students here because Brazil is not, how do you call it? It's high tech. It's a high tech country today. It's not, the Brazilians have a problem, and maybe talking to the students now of the Biophysics Institute, this is called complexo de vira-lata. They think that they're not worth it because they're from Brazil. Well, Brazil is no longer a third world country in that sense. High tech being exported all over the place. But going back to 1959, which was when we were talking, my father was talking here to Jânio Quadros. Unfortunately, the politicians of Brazil at the time decided to nationalize the Fokker industry, that was in Galeão in Rio de Janeiro. And so this is why my last year in Brazil was in Rio de Janeiro. And then so my parents decided to go to Holland rather than. So instead of going, because it was nationalized, there was no future in terms of, and the children were going to secondary school. So instead of going to Dom Pedro II in Rio de Janeiro, for which I was already admitted, I went to a school in Holland. So back to Europe. Now we have 2000 here, 1960 to 2017 in Europe. That is 57 years. Ooh, a long time. And here this that we met in Durban at this international meeting. It was the city of Durban was so dangerous that in going from the hotel on the seesaw side to the convention center 5-6 blocks away, you couldn't walk because it was considered too dangerous. So you had buses, and we were bused from one place to the other, and so yeah. Like it or not, and suddenly there's these two Brazilians in front of me, and they're speaking Portuguese, and then I started to interfere with the discussion, and that's when I met Professor Vanderlei de Souza, and he then asked me, "Are you giving a lecture?" Yes, I'm giving. So he came to see that I remember seeing them in my lecture, and he invited me to come to Caxambu to give a lecture to the Brazilian Microscopy Society in 2003. This is okay. So that was but so back to Europe and the whole education and here the obsession with lenses and optics and things like that went on and on. And so here we have at the university now in the Netherlands, in Groningen, here's a transfer function. Here Fourier transforms a plane wave into a point. But if you have a little scatter in the object, then that will give rise to secondary waves, and that will become a plane wave. So you have a plane wave, a constant Fourier transforms to a delta function, and vice versa. A delta function, a point in the object, transfers to a plane wave or constant in the back focal plane. And so this is nice. And if you have two of them, then you have a double Fourier transform. So the whole imaging, the whole idea of imaging becomes just this is the idea of linear imaging. You have a Fourier transform and a second Fourier transform. Of course, there are magnification differences, but this kind of thing helps you describe everything that is a microscope, a telescope, a radio telescope, whatever has to do with a photographic camera. All these things are covered by this type of mathematics. So and then Fourier transform of the object is in the back focal plane, and that Fourier transform is the image. Here comes the limiting aperture. If you close this aperture, then suddenly your numerical aperture of the instrument reduces, and the resolution, the maximum resolution, the instrumental resolution that you can becomes worse. So that's famous formulas by Aber and Rayleigh and people like that. So here comes a list of those heroes of imaging: Aber, Rayleigh, and Fritz Czernik. I'll stick a little bit. The idea of this double Fourier transform is more in the sense of how Fritz Czernik was thinking than the other two. But and he was a theoretical physicist, but he a brilliant tinkerer also in optics. And all he did is put a tiny little piece of glass to change the phases of the zero-order beam to the diffracted beam, and that allowed you to see bacteria swimming in water and things like that. So the idea of linear systems and the idea, the perfect understanding of the physics behind it allowed him to invent the phase contrast microscope, for which he got the Nobel Prize in 1956, if I remember correctly. So anyway, so this was my optics and the first papers that I wrote, background, and the first papers that I well, it's a theoretical physics, so there's a lot of formulas in here. Formulas 37, 38, 39, 39, 40, and then more formulas, see 60. The whole paper is absolutely loaded with formulas. But what I really want to tell you is this here in the acknowledgements. I would like to thank the members of Professor Ferveda's group for commenting on the first version of the manuscript. I especially thank Doctors Andre Hauser for pointing out an important error in my first version and for giving valuable suggestions. So I made a mistake, and I am apologizing for this, or I'm just accepting the fact that I made a mistake and correcting that. And I also acknowledge the discussion and correspondence I had with Dr. Joachim Frank here. That was actually on this topic of coherence. He had a paper that was incorrect. But okay, that still is incorrect. That's a different topic. That's a topic for another time. But so what I'm trying to say here, I'm going to be quite critical in talking about various other scientists. I'm going to also be very positive about other ones. But I think that's important as a scientist, that if you make a mistake, that you should be able to apologize for this. And so the first paper that I wrote all by myself was I have this apology that I wanted to show it. So here comes the instrumental resolution I talked about. Yes, so the limiting aperture will cause the resolution and the idea of the linear system with Chernyk's phase plate. Now, the linear system is that the object, Fourier transform of the object multiplied with the transfer function here, or the phase transfer function here. Here a simplified version of it. So you have here an object, some linear device. It's actually not only for images, it can also be like an amplifier in 1D or a tomographic machine in 3D. So it covers a whole range of imaging devices. So here we have this beautiful portrait by Richard Avedon of Marilyn Monroe. And so here the idea of transferring the information linearly. When you transfer the information, you can compare the input image with the output image of, for example, and see how similar they are. And the most used formula in this presentation today, there are quite a few formulas, but they're all very simple, is the normalized cross-correlation coefficient. So how do you define how similar these two? How good is this imaging device? How similar is this to the input? And so for that you can do a correlation coefficient. And the correlation coefficient. So this is image number 1, and this is image number 2, and these are all the pixels. So you're running through all the pixels of the image, and so this inner product between these two images or vectors, they will it's a pixel by pixel multiplication and a sum. And to normalize it, you use the power in each of the images. So if the images are identical, then the output of this thing is going to be +1, because if this is identical to that, then and you divide by the power of both, then it's very simple to verify that everything is 1, and so the maximum value, if these things are totally identical, the correlation coefficient between the two will be +1. So here we go. The signal in, Fourier transform, blah blah blah, signal out, and cover this by so-called transfer function. But you can also have this. So this transfer function suddenly is just multiplying everything by -1. Now, did I lose all the information only because I have a negative image? No, there's no information lost, because everything is I multiplied with -1, then I have exactly the same thing as I here. So there's no contrast reversal. Will have no influence. All the information is there. So what am I saying? Then that means that the normalized correlation coefficient, if the two they are identical, but one is also plus and the other one is always minus the other one, then it's very simple. This is all positive. These are squares. So the maximum is then normalized to -1. So you have at +1 and at -1, you have perfect correlation. In one case, it's perfect anti-correlation, but I'm just trying to say that this metric of having a correlation coefficient, -1 is just as significant as +1. And so here is a spit out of a bit more in detail. Here we have Marilyn, and then a Fourier transform of Marilyn, low pass filtered by a transfer function. And so you can see that the high frequency components have been suppressed here, and then your Fourier transform back to real space, and you see a little bit of a blurry version of Marilyn. And so that is a linear system. This is what Fourier optics is and what a filter does to your image. And this is just exactly the same thing, but in a mathematical formalism. So you have the object coming in. This is now called the convolution with the point spread function, and that gives the object going out. And the best way to calculate it is just through the Fourier transform of the object times the transfer function is the output, and you Fourier transform back, and you get that. Now, this is, of course, in a model calculation. And the other one, this one, is also a model calculation, but the model now is an electron microscope. So it's difficult. I don't get any feedback There's no laughter, no. That's a different style of presentation. But well, maybe after this COVID crisis, we can go back and well, I don't know. Can there be questions? Can somebody answer? Can there be questions in the middle of the lecture? Is that not the way it is?
So usually the way we do is that we write down the questions, but if someone wants to interrupt to address questions, I mean, they are free to go. But usually we avoid doing that.
No, I understand. I appreciate that. It's just that as a speaker, this is my first larger lecture, it's a bit, but now applied to the electron microscope. So here's an object, this so-called Siemens star. It's a beautiful test object because you have high frequency information here, and you have low frequency information there. You can Fourier transform it. And the electron microscope will impose, depending on your defocus, and all kinds of oscillations onto the Fourier transform of that. And that then, when you transform that back, you can see clear these zeros in the transfer function where the contrast reverses. And so it's all exactly the same mechanism, like this under this, how do you call it, this low-pass filtered version of Marilyn Monroe. But here we're talking about an electron microscope. And but there is something about this way of thinking, linear thinking, this linear imaging device. And here we go again. The traditional way of linear signal processing is that you assume you know everything there is to know about the object. And then you Fourier transform that, and then you know everything about this imaging device. And then you can predict what the image is. But in reality, the reality is very different. Of course, you have no idea what you have in your microscope. And even, I mean, just in general, you only, you as a human being or with eyes, you're seeing the information that falls on your eye, in your eyes, and your in a microscope, you have no idea where the data comes from. All you have is the information that comes out of the device. So I told you here that there was an image of Marilyn Monroe at the beginning that we use as a test image, but in reality, it's very different. And of course, you don't know beforehand. And the other thing is that you will always have, the output image will always be worse than the input image. You have noise added to it, yes? And so it's no longer the same thing. And so we actually have to go back to our basis and think about the linear system. So here we're talking about the upper resolution criterion, Rayleigh criterion, things like that. And the microscope has a limit, yes? So because of this aperture and maybe some aberrations. But this all is a property of the instrument. You can have your microscope in the cupboard and the numerical aperture of the lens is the same, and therefore the resolution limit of that machine, whether you use it or not, is the same. Now, that's of course not the reality of microscopy. The reality of microscopy is completely different. You have an instrumental resolution, but there is no guarantee that you will actually have that resolution represented in your image. I mean, if you forget to switch the light on of your light microscope or your electron gun, then of course nothing will arrive on the other side. So you have the instrumental and the resolution will not be the same. And this sounds a bit like pedantic, but it's the reality. You don't know what's in your microscope. Well, you have samples. You hope that there's some good stuff, but of course it's getting very rapidly damaged by the electrons, and so all that you know in reality comes from the noisy output images. You have no idea what's at the beginning, so you want to understand that, but you can't see it. And so this is a real problem in the imaging paradigm is that this the image is the result of that you should have. People think that you should have on the output the same resolution as the input, and that's not necessarily the case. That's actually quite certainly not the case. And so, but what you can do, you can take multiple images, and so let's then compare them. I've already shown you this correlation, normalized correlation coefficient between these two images. I have here a simplified version of that. It's just not normalized, but it's just, the thing is here is that you have image 1 times image 2. That's the crucial thing. And then you can normalize it. Yes, of course you can normalize it, and that keeps things well behaved. But how good is, if I want to use this as a metric to see how good my result is, then I have a problem. And this correlation coefficient will be a single value between these two images, and it has very, very little value. And why does it have very little value? Normal images like a portrait of a person will have very strong low frequency components. Here's the power spectrum of that. So you have a lot of the low frequencies, but nothing in the higher frequencies. And if you do the correlation coefficient, then all these big black areas or the white areas will dominate the correlation coefficient, and you will have a value that is very high. But the fine details like the hair, that they hardly play any role because they have a very low power in the result. So this is not a very good criterion, the real space correlation coefficient. And so this is where we came up with this Fourier ring correlation, where you, instead of comparing this in real space, you compare it in Fourier space and do it frequency by frequency, and normalize also the power frequency by frequency. So this is the power distribution. This is actually not from this experiment, but I mean, in many cases, I'm just explaining using these images, not necessarily connected from one experiment. So the correlation coefficient is not good enough, and so we come up with this Fourier ring is the normalized correlation coefficient that's because completely overwhelmed by low frequency, so it has very little explanatory power. And here in Fourier space, you go then rings in Fourier space, and in different levels you have. So, but this then becomes a function of resolution, and this is just a constant. So okay, so this helps us to understand images like that, and to get to comparing that, we have an idea, and you get these nice curves from that. So here you have the two images. You have the Fourier transform of two images. You calculate the Fourier ring or Fourier shell correlation. Fourier ring is in 2 dimensions, and Fourier shell correlation is in 3 dimensions. And so in 3 dimensions, each of this red ring becomes a sphere, a shell, and this yellow becomes a yellow shell, but the formula stays the same. So here we have these normalized correlations. This is also just a normalized. I should say that this is, of course, in Fourier space, and in Fourier space everything is complex, but the structure factor here and the structure factor there are plus minus of each other. So because of the Hermitian symmetry, at least the imaginary part. If you, by the time you integrate this around rings, everything becomes real. So it's just a normal correlation coefficient, just like the cross correlation coefficient we had in real space. And so this then, and here you can see where this curve actually came from. This was from a paper 35 years ago on the 30th ribosome subunit that together with Marin and Stoeffler. So you then see that this correlation curve drops, and to a certain level at the time, 17 angstrom was a very high resolution for a 30th subunit. But this has now become the standard in 2D and in 3D. And here we have a virus structure, just an alpha virus structure, which could have been a this is actually the Fourier shell correlation from hemoglobin. So I'm just using these as models for the calculation. So you have two 3D structures that you have two half data sets, like two different noisy images of Marilyn Monroe. We have two 3D structures calculated from half the data set, and we compare them to each other in Fourier space. In this case here, Fourier shell correlation, so this is the shell, and we calculate these cross correlations, and at low resolution, they correlate very well, and it drops slowly down, and these are different little thingies for specific for the warm hemoglobin, actually. But so this is you start off in the Fourier shell correlation value close to 1, then it drops, and then it cuts this threshold curve here, and then starts also. With your morning coffee, you can check what's happened in the field of cryo-EM by just looking for Fourier shell correlation. And then you have in Google search for Fourier shell correlation plus cryo-EM, and you get all these curves here. And you can then click and look at that. And so that typically most of the structures are accompanied by these curves. Nowadays, people are doing that less and less, actually. But there is a serious problem. You can see here that here, for example, there's a line at 0.5. There's a line of 0.14 here too. There are all kinds of this here. And so let's grab one of these things here. This is from Sriram Subramaniam. What was he looking at here? P97. And he had a resolution here. This is a few years ago, so 2.3 angstrom was a record. But here you see then the Fourier shell correlation. You see these different thresholds. And one group says, oh, well, this is the threshold. This is the resolution. This is the resolution. And this is friend and foe. I already defined that to be wrong much earlier. After all, the Fourier shell correlation is something that we published ourselves more than 35 years ago. And these fixed values were all wrong. You have to do the combination of search Fourier shell correlation plus cryo-EM, because if you don't do that, you just look for Fourier shell correlation, you get here, what is this? The Forel Stewardship Council. And so it's a registered trademark. I don't know if they registered their trademark after or before 1985, but okay, this is a, but the thing is here that these thresholds, the fact that you have this discussion about what the resolution is really a problem. Now, and then that enters into the realm of sloppy statistics. And as I start off in the beginning. Now, the sloppy statistics, this is an example of sloppy statistics. It's not defining sloppy statistics. So that you assume that you have two measurements of the same thing, so signal, and each are deteriorated by noise, like the images of Marilyn Monroe. And then you can compare the two by correlation. So here you calculate the correlation between these two, the inner product of this vector and that vector, and then you get signal plus noise 1, signal plus noise 2, and you calculate this is A plus B and A plus C, and the cross product of these things are just so standard that everybody knows these things. So we have the power S squared, that's times that, S times N2, N1 times S, and N1 times S2. Now, the big problem that happens now in electron microscopy or in all fields, this was not even started off in electron microscopy, starts in all fields of signal processing, is that people say the signal and the noise are not correlated. So we can leave that out of the equation. And that is a disastrous mistake, a pretty disastrous mistake. And so here we see this first time that is by Bershad and Rockmore, where they're doing this signal plus noise 1, signal plus noise 2. And from that, they come to a signal, to the correlation between, what they're trying to do is to figure out from the correlation, which we can calculate these correlations here, try to find out what the signal to noise ratio is of this experiment. And so that's what they're doing. But there are all kinds of boundary conditions that they assume that it's just wrong, and simply wrong, because here that's explained here, and that there's a paper coming out which which will explain it even more, but there's so many papers that we already have in the past, so it's easy to find these things. And so they have this function, this formula here relating the signal to noise ratio to used all these assumptions that were built in by these mathematicians, these orthogonality assumptions here. And but these mathematicians already used orthogonality assumptions that couldn't be used. Now let me try to explain that what that is. The first time I used this is when we were the presentation of the Wiley Award in 2017, and the other awardees were Joachim Frank and Richard Henderson. And so here we are, correlation, this is now in Fourier space, inner product between this information and that information. And so you have the sum, and you have these cross terms here, and signal and noise are independent, and thus the cross terms are equal to 0. So that is what people assume, and that is actually very fundamental, really wrong. That is now that is statistical rubbish, and now and that has serious consequences. I'll show you that. So if you have an inner product between signal and noise, inner product can be images. So we have here Einstein and we have noise. Then the inner product between these two will be 0 on average, but not in the individual case. And that is, you can, of course, all this random, you also noisy fluctuations around that. So this is a little model inspired by Nico Grigoriev. And so this is on, but if you say then that this is always 0, and if you take something out of the formula, you take it out of the formula, it means then that suddenly you're taking that not on average, but you're saying that this is always 0. And it isn't, because on each individual case you have independence and orthogonality. Now, the model that I used there in New York in 2017, I need to now adapt to Rio de Janeiro. So this is, let me call this, so we have a young couple wildly in love that were now renting an apartment or buying an apartment in Ipanema, where I went to school 50, 60 years ago. So that was the international school. So here we have this couple in Ipanema, and they're wildly in love. And if one group, so X and Y, these are not chromosomes; they're just individual abstract names. Yes. So if we have this couple in the beginning, they move in. T is 0 years, so they just moved into the apartment. Then bathroom and bedroom and things like that, hallway, living room. So what happens is the following: if in the beginning here you have person X and person Y watching the same novella, the same soap opera on the same channel, and sitting close together and fantastic. This is wherever Y is, if X is doing the dishes or Y is doing the dishes in the kitchen. Oh, the kitchen was here, sorry. If X and Y are doing they're always, the other one will be drying or helping or things like that, or in the bedroom, both are in the bedroom. So wherever person X is, person Y will be 2. Then you have the distribution function of person X and Y over this apartment, and you calculate the inner product between the two. Now, in the beginning here, there is, oops, something went wrong. In the beginning, the inner product will be 1 because they're always fully correlated. Now, this is in the beginning, and then 7 years later, they still live in that same apartment. And if now somebody is watching TV, a novella on TV, the other person may be watching on the iPhone a completely scientific program or something completely different. And if person X is doing the dishes, person Y may be watching the sunset here from the balcony So it's entirely random. And then you have 1, 2, 3, 4, 6 possibilities, I think. Yes, 6 possibilities. Then the chance of them being at the same time. And then, of course, 7 years later, then if person Y is in the living room watching something in the corner here on his iPhone, the other person will be watching in the bedroom on a different channel on the Android phone. And so wherever person X is and person Y, so this is time for them to cancel the rent and go each their own way. But so here now the inner product, the distribution, if X is in a room, then Y is not in the same room, and vice versa. And that means then that the distribution function of one and the other ones are completely orthogonal, and the inner product is 0. So the 0 between orthogonal and random, this is independent or orthogonal, that's what this is. And this mathematical error was made by mathematicians already in the very early days, and then was applied to electron microscopy by microscopists. So let's apply it to cryo-EM particles on a grid. And so the mathematician said, first assume you have a spherical column. And then, so this is typical. The mathematician has a nice idea plus boundary conditions that are not necessarily realistic. And then comes a physicist that the mathematician has his head in the clouds. That was not, that was the story that I told here this was 2017 during the Nobel festivities. I had a lecture talking about this. Okay, so now we go to the next phase. And that is now after contacting Brazil back again, thanks to Vanderlei, come back to Brazil and helping setting up a facility here and teaching people. We had a Brazil school where we've started doing that. Rodrigo and I started doing that in 2005 already. So there's now 8 of these schools, and they become very popular. There was supposed to be one in November now, but it's canceled because of the COVID infection. But that's one thing, teaching new people, very important. The other thing is we're working on the facility, and Rodrigo Portugal did really a very, very massive job to get the microscopes in. And here we see him pulling in the Cryos microscope. This was at the end of 2018. And luckily he had some help from friends outside because it's a pretty heavy machine. And but now at least we now have the very first Cryos microscope in Latin America. And the Cryos became operational in December of last year. It took about a year to get it actually done, all the parts together, and there were some real serious technical problems. We spent months and months full time just to resolve those problems. So the first data sets were collected now in December, and the computer went out here of the frame, but the computer cluster has been in operation. That's already during the pandemic. So here, but anyway, in spite of that, we now have the whole pipeline started, and so here is the Cryos operating, collecting data. In this case of a virus, correcting the transfer functions, calculating 3D structures, refining that, and so on and so forth. And then from that we do these resolution maps, as the Fourier shell correlation, as I have explained to you. This is from hemoglobin, but I mean it doesn't really matter. So it just shows you that so this is now in operation, and we're tired just because of the incredible effort that everybody had to do to get to this point. A bit more about the statistics of the whole thing, and then comes really a very important change now, and that is I'll call this sloppy statistics 2. And it's the same thing as sloppy statistics 1, talking about these cross terms. And again, this no longer the same mathematicians that we're talking about, but this is quite a serious matter. So, and what did we all do wrong? In the other one, I said, what did we do wrong? It took so long to find these problems because they're so built into your education, that was the first time I show you the slide. Maybe I can go back because I myself forget. Yeah, see here, I didn't emphasize what did we do wrong, because I say we. This is what I said there in Stockholm in 2017, because it took a long time to really realize what went wrong here, and are not. But now let us go back to these issues of signal to noise ratio, and I started the very beginning, signal to noise ratio. These calculations that people were making were trying to estimate the signal to noise ratio from the cross correlation, and the signal to noise ratio is directly related to the information content of that you can, or the information capacity of a channel. So information and signal to noise ratio are two things that are very closely coupled. And now we're no longer talking, we're now talking about mathematics, not from the 70s, but we're now talking from 1948 and even earlier than that. So here is the something that I found on Twitter. So this is a classical picture of Shannon and his transfer of information a diagram, where you have a signal coming in and an independent noise source that enters into the channel, and then you try to decode that coming out. But what I really liked from this tweet is that Shannon information can only be lost, never gained. And that's oh, sorry, that's just some propaganda on the streets. So if it gets to be very disturbing, I have to close the windows. Please just tell me. So Shannon's information here is based on this simple diagram, this communication channel, and here's the signal to noise ratio. And again, we have the same problem as we had earlier with our image system, is that we have no idea what comes in. And in this story, where you speak of signal to noise ratio, you need to know the signal before you do the experiment, and to be able to say something about the signal to noise ratio. And so the problem here comes from on a different level. There's the that they came up with, and that's this here. Alpha is the signal to noise ratio. It's rho. That's the cost. This is the correlation coefficient divided by 1 minus the correlation coefficient. And so this is what Bershaw and Rockmore published here, and then it was copied into electron microscopy by Frank et al. And then some mathematics behind it by Saxton. That's all discussed in this paper, and way beyond the scope of this lecture right now. But so I mean, this has been going on and on. This is a paper from the group of Frank, 2009, and here we make work in this the signal to noise ratios and spectral signal to noise ratio. Anyway. Here they're claiming this relationship here between signal to noise ratio and cross correlation coefficient. But there's a real problem with that. This relation is fatally flawed here. What happened? The cross correlation coefficient, I've been telling you that this can have values between -1 and +1. But the signal to noise ratio, as it was defined in the past, is always positive. It's the power of the signal divided by the power of the noise. So these things, this one can be positive and negative, this one cannot. So if there is no signal, then the cross correlation between two measurements will oscillate around 0. And you have negative values for CCC, small values, but negative. So suddenly this translates to negative values for the signal to noise ratio. So we have a serious problem here. that is here, this physics paradigm that I started off with here, the signal to noise ratio is positive. And information, the way Claude Shannon formulated, is also only positive. So you can only collect positive information. If you put a telescope and aim it at a dark spot of the sky, you have no idea what's on the other side, what you're going to collect. But by this definition, you will always, there will be some signal maybe, and there must be some signal. You will be collecting positive information because it can't be negative. And that's really a very, so let me, so this is, we're now going into mathematics and what went wrong with mathematics. So the way my father would formulate this, mathematicians have their head up in the clouds and not necessarily their feet on the ground. And the physicist has, they're both, they understand the formulas and they have their feet on the ground. So the biologists have their feet in this mushy stuff here. Yes? So biophysicists, I don't know what, but let me simplify things. Let me take the biology out now at the moment because we're really just talking physics here. And we want to talk about the signal to noise ratio and about the information. And as I said, the signal to noise ratio is per definition always positive because you have the power of the signal divided by the power of the noise. And but you when you do a measurement, you have no idea whether there even is a signal in there. Yeah. So here's the channel information capacity. Again, just positive. You can only collect positive information. But and I've talked about that, the cross correlation. You can actually always get a measurement. The other case you can't because you can't measure the signal to noise ratio because coming out of some noise oscillating around zero, you have no idea that there will be a signal in there unless somebody told you beforehand. So here's the normalized cross correlation coefficient. Here's Fourier shell correlation. It's in different space, but the idea is the same, and the normalization is the same between -1 and +1. And what did I change here? Okay, so the cross correlation coefficient, it has a real problem because when you're very close, I showed you that was the negative image of Marilyn Monroe that has exactly the same information as the positive image. You can multiply by -1, but the cross correlation does not show that. Now, there is and the other thing is that when you get very close to plus, and so there was a mathematician here, Fisher, who suggested to not be bothered by these limits. The normalization makes it force it, these values to be between -1 and +1, but this one then suddenly spreads it out and allows you to, so I did too much here, but this one's, I don't know how many slides I kicked out of order.
Professor Van Hill?
Yes.
Yeah, so this is Fabio Gomes again. I just would like to point to you that we have been over a little bit more than an hour.
Okay.
So, I mean, perhaps some of our colleagues might need to start leaving soon. So if you could just try to...
the course comes now. Sorry, but I appreciate that. So let me...
This is wrong information also. I was not aware that some of our colleagues could be a little bit short of time and things like that. So
I thank you. Okay. Yeah, this is a problem if you don't get immediate feedback. I now have to get my PowerPoint back up. Hold a second. How do I do this?
We can go to...
see it again?
Yeah, good.
Yes, okay.
Yeah, perfect.
So, yes, I am where I wanted to be. And to avoid that, you get, okay. So I appreciate it. But the crucial point comes here still. It's a very long story. And so here we have this Fisher transformation. And what we're doing now is doing exactly the same Fisher transformation in the case of the Fourier shell correlation, Fourier ring correlation, and that really changes everything. because now we have information in 2D and 3D that we can actually use. So here is this is the same formula in two different forms, and so now we have the Shannon's information capacity, but the Shannon's information capacity was limited from starting to 0, and so that was the serious problem here, and but so we have the Fourier shell information just for comparison here. Now the 1D version of this, I won't discuss that. That's going to be extensively. And now we come to really the biology. I'm sorry that it took a bit long. We're using this to do the overall resolution between these structures, but and so you do that. That's what you have these three-dimensional structures here and compare them in Fourier space. But what you can also do is is to do them locally, and locally is very important. And this is what I'm trying to get to. And if you do them globally, you can get these. This is the Fourier shell correlation. The new metrics now. The new metrics here, for example, there's no information close to the origin. So this is what people think of in terms of resolution. This is the half-bit Fourier shell correlation, and we doubled the number of particles, or see the measured particles here, and we see how the resolution changes from here to here to here. And now close to 1, there's virtually no information. But when we now use these resolution, these Fourier shell information metrics, then suddenly everything changes. You can actually see here how the total amount of information goes up as function of how the total information goes up as function of the doses, so or as of the number of particles. And so you can actually see that there's a lot more information here than there is here, and that's a much more powerful metric than just that information metric. And so now that then you can use also locally, not just also do it locally. And the local one went to the different. Okay, so and when you do this, then you get suddenly you can map you get the local information. This is the wrong slide but they got out of order. So the local information here you can now use to map the color of this the structures that you have, to map the information density that you have inside the structure. So this is exactly the same structure that you would have in black and white. Here we have the hemoglobin structures. These are stereo pictures if you manage to see them in stereo. And you see here, these are beta sheets, the very hard core, the rigid part of the structure, and these glycosylations growing out of them. And here, if you change this, the threshold, you can see the glycosylations grow even more. And so, or here in the, but so this is our experiment. We have done it. This here is looking at the database. We're looking at these things in the database. The structure of this is from the group of David Wiesler, and this here, the other one is from the group of John Briggs, I think, I remember. And you compare them to each other, and suddenly that shows you the glycosylation in one, because you're looking at the cross information, the local information that isn't predominant in the other one. And so changing the threshold, you can suddenly see these glycosylations grow. And that really is, and that brings me then to the end of the story a little bit. And so this is the one that I showed you before. And so this will rotate and this will, but let me go through this one if I manage to. And here we have more, we can change the threshold of the glycosylation, and we can see more and more the sugars that protect the virus from. Let me go to the last one here. Yes, and I'll show you this as a. So here we are looking at glycosylations from structures of the COVID virus, that COVID-19 virus that we haven't that we had nothing to do with. We just downloaded it, and we see here like these end glycosylations growing out of the structure, and we have we can actually even cover it completely with this is here the more visible part that is infectious, and that doesn't have as much glycosylation stuff. But we don't exactly know because we haven't used, this is not our own experiment, we're just interpreting data from others from the database. Let me just, okay, then 2 more slides or 3 more slides. I'm sorry that I'm going over time because this is really important here. So the theoretical aspects of information. So let me. This is what just. So here, this statistics, what I call the marble statistics, but it's combinatorial statistics, where you have like a coin and it has only two possibilities, the up or down side, or you have marbles in a bottle and there are 3 different colors, or you have letters in the English alphabet and there's only a limited number. And this is the type of statistics that is behind Claude Shannon's information theory. And so he was very good at combinatorial things and decoding. This is an Enigma machine, but that's not the one he worked on, but he did work on coding during the Second World War. And but this is the type of deterministic statistics. The other type of statistics that we're actually looking at with these products is the wave particle duality statistics. And so you have the fantastic young interference fringe experiment where you have electrons and they interfere with each other. So this is the real statistics of counting the arrival of the electrons and counting and collecting the information in practice. This here is from my master thesis 45 years ago, where we did this biprism experiment here. So this is the statistics of the physicists, or the uncertainty statistics of this kind of physicists here, like in the Solvay conference of almost 100 years ago. So we have done that in terms of 1D and 2D and things like that. And let me then thank everybody who contributed to this. Michael Schatz and Ralph Schmidt, they have been supporting. Michael Schatz is the co-author of the paper, and Ralph has done a lot of the mathematics or the computing support behind it. Rodrigo Portugal, Sayan Vera, Sayan Barca, Helder, all these people have contributed. George Arauz contributed in the very early phase of the process. And yes, I think I should stop here. There's just too much material, but I really, I hope I try to convince you that we are really trying to get to a different type of statistics and a different type of metric of information than the metrics that was proposed here, which is the metrics of deterministically knowing your input signal. And it doesn't apply to what we have, the understanding of the harvesting of new information. So thank you very much. Let me try to see if that's a problem that one doesn't. Yeah, I can hear you.
Okay. Well, thank you very much. That was very impressive work. And
I was also very happy to see that also in Brazil we are having some infrastructure that is being built upon that, and we are actually hoping that we have more people working with single particle here in our country. We really do appreciate your help also on that. So we have a few questions coming from both Google Meet and also on YouTube. We are a little bit of restriction on time, but hopefully we'll have time to address some of those. Okay?
Okay.
All right. Okay, great. So Professor Kildare Miranda was asking if it's possible to combine single particle approach, specifically using robust statistics, with EOS or EOS and ESI to retrieve information on the chemical and elemental composition of molecules.
Well, yeah, you can combine. Yes, I guess one can. It's a matter of statistics, yes, because and these information metrics really help you to understand these things better also. But it's if you have EOS, then you have not three-dimensional, you have four-dimensional information, and so you have color, so to say, in each voxel or in each pixel, and so you have to play around a little bit with the parameters, but in principle, the software and the ideas are the same. Yes, it's like 2D and 3D of these Fourier ring information, Fourier shell information. They're not different. So it's just one is in a shell, the other one is in a ring, but the basic statistics is no different in those cases.
Okay, thank you. Rodrigo Portugal was asking if you could comment a little more on the application of these methods on comparison between different structures of the same molecule.
Yes, so that's actually we have done quite a bit of that already. This is the structure that I've shown of the SARS virus, SARS-CoV-2 virus. They are actually comparing two different structures, because when we have the data ourselves, what we would first thing, that is already a cross comparison between two different structures, or you have flexibilities. And so this is a very powerful technique to really localize these different areas, and it's not restricted to macromolecules at all. You have tomograph. So this is, a section that I haven't shown you because there's just too much. But if you have like a patient, you have multiple images of the thorax or something, yes, in tomography, then the part that will be blurred is a beating heart, for example, yes. So that will be the local cross information will be different there because of the blurring. So, or the texture of the liver is different from the texture of the spleen or of the stomach, and these textures will be characteristic. So it's not restricted at all to electron microscopy, yes. So tomography, but all 3D geophysical imaging, you can apply to very many different things.
So I will take this hint and ask a question from myself, actually. So concerning the glycosylation, which direction do you think this is going? Do you think that you'll be able to see difference in the amount of glycosylation as well as the organization, the types of glycosylation? How far do you think we can go in the near-term future?
We have already papers in preparation where we're actually looking at the glycosylation of a system that we here. I was maybe a bit too much for this audience, looking at the image processing or the signal processing aspect of things and how information is used. And if you use it properly, you immediately see the glycosylation, for example, which is something you were not looking at, and it's not even your own experience. It's not even your own experiment. So yes, but glycosylation, I don't have to tell you, is something very complicated, and these viruses even use some of the sugars that are inside the host to hide themselves from. So the virus has a different sugar coat in different hosts. But yes, we're seeing them. We can understand them. You can see to which level they go, and you can also see the gaps in between the glycosylation, so that you know where to target your antibodies, your monoclonal antibodies against, or polyclonal. But I mean, just your what shall I say? Yeah, your vaccine, so to say. Where do I have access to this nasty bug? Absolutely, yes. So
okay,
what we couldn't do here is we would normally look at, so you have two data sets in different conditions. You would look at these the information in each of the two internally, and then do the cross comparison between the two to understand the structural differences that you have in the glycosylation or in the molecule itself. So yes, it just opens a whole new group of techniques to understand biological problems of this nature.
Wow, that's very exciting, very interesting. So Mark Rodriguez was asking, so are there proposed metrics to determine resolution in electron microscopy that don't use either FSC or FSI? And he was also asking if you could tell a little more about the criteria to define what is acceptable based on FSC and FSI.
Well, the good thing is that FSC is a little bit more, is just gives you one value. And the one value is just what's happening at that resolution. It's very noisy. The FSC gives you the integrated information. You saw the curves go up. If you increase the data set, you see the curves go up over the whole thing, over the whole range. You can see the whole range of spatial frequencies go up. I think we're too much focused on a single number in terms of resolution. Resolution is not a single number. It's not what you're interested in. You can have a structure that has only very high resolution information and is inconsistent in the rest. And then you will go to that threshold and find it there. But that doesn't help you to understand your biology. What helps you is the total amount of information. I mean, if you, for example, and it's not electron microscopy. You can have whatever calcifications in the human brain, and you would like to see specific size of calcifications. How much information do you need in what frequency range to pinpoint these calcifications in a patient? And and that's not a matter of resolution. It's the amount of information that you collect around locally around these things, and that will then immediately visualize the. I've been talking too much. Sorry.
No, please go ahead.
And that will allow you to define then. Here is a patient, and I need to have so much information in that frequency range to say that this is a malignant tumor or this is whatever the source of in the right frequency range. Over that is important.
Okay. So Eugene Pitko, and I hope I'm saying that right. So dear Marin, what do you think of the recent results on atomic resolution cryo-EM? Isn't the CC bond length, he's referring to 1.4 angstrom, a good way to test current approach for estimation of resolution?
Well, the paper will be out in a few days, but and I'll show it. There's a real problem with that, because what people are doing, they're doing refinements of high resolution components of the data and trying to match that to an atomic model. And so that's an iterative procedure. That iterative procedure in trying to match that makes it's per definition a biased procedure, and it leaves the field of linear imaging. So the concept, like the Fourier shell correlation as we defined it more than 35 years ago, that cannot be applied. This is the very serious problem, because you have these different groups doing refinements. And if you do these refinements and leave the linearity of the imaging, then you can't compare the two to each other. And that's one of the big dangers. Like if you have two different structures from two different groups, then these information measures show you that you can add them. So they would complement together. If you have group A and group B and both have a structure at 2 angstroms, then the total information from the two should give you to 1.8, say, or something like that. You should get better, more information, because they're independently collected information. Now, if each of these groups finds a non-linear refinement and trying to fit and to see the holes in the tryptophan, and then even the difference in orientation, very close to the Nyquist frequency, that really causes total non-linearity, and you can no longer compare the two together. So the linearity allows you to join the two and work together and find out more, whereas these high resolution, the metrics that they're used are not the correct metrics, and they leave the realm of linearity. As I said, these issues are discussed in great extent in the paper that is going to come out soon.
Okay, we'll be looking forward to that, and I will take your answer, and then I will use that to jump to Marcia Atia's questions. So basically, when you're talking about glycosylation, for example, there's something you already know that is on the structure of the protein, but how far can they are around?
Say that again, please.
So how far could you think? How far can you go to use cryomicroscopy, concerning that it can give you some kind of noise to obtain information about images or structures that you do not know that are already there in the first place?
Yeah. So this is the Einstein in noise problem. So I mean, if you look for Einstein in random noise, you will find Einstein in random noise, and the more you look, the more similar areas that look like Einstein you will find. You can add that together. That was actually a theme from Michael Schatz, the co-author of the paper, thesis in 1990, 30 years ago. And so you always need a validation, independent validation, and you need. But I think these metrics of information really help you to quantify that. Yes, I mean there have been fights in the literature of people who have been looking for specific structures in the data and have found those structures and have published them as high resolution structures. So, but I mean, there's a little without going into that will be in the paper as well, and all the links and the paper is 45 pages in single space. So it covers a lot of ground, because there was simply a lot to be covered in terms of a correct using of information and image processing.
So it will be a slow read. We'll take the time.
Yes, you need 2 week vacation to read it.
Okay, that's great. So I'll start moving to questions related to the future of cryomicroscopy, as I think that's a good way for us to start like wrapping up. So still from YouTube, Sayan Bhakta was asking if there is any future to look at smaller modifications when compared to the ones you find on glycosylation.
Say that again, please. What small?
So smaller modifications compared to glycosylation?
Yeah. Well, I mean, yes, you will find. I don't exactly know what he means here, but yeah, yes, that adds to the complexity, but you still need to, how do you call it? You need to do these. You need to validate whatever you do, And so you need to really be convinced that you're not looking for Einstein in random noise.
Okay, perhaps Saya wants to complement later and give a few examples of exactly what it was meant in the question. But in the meantime, Kildare Miranda was asking, so what comes next in terms of cryo-electron microscopy?
My lecture now was not necessarily about cryomicroscopy. It's about but it's about the whole field of collection information, and so the changing of the idea that signal to noise ratio is not information, and even Shannon's information channel capacity is not about collecting information. It's about not losing information that you store onto a hard drive or that you send to a. But in terms of electron microscopy, I think we're learning. There are, I think, some wild growths in electron microscopy at the moment where people are really just leaving logical. They need to be open to understand. I mean, there are serious mistakes made in the literature, and people are simply ignoring that. And the metrics that are now being used to define what the resolutions make no sense. So you cannot compare the results to each other. So I think at the moment we need to go through a phase of just consolidation and just how do you call it? Calm down. People want to go to 1.7 angstrom, 1.3 angstrom, 1.2 angstrom, but they're using metrics that make no sense, that don't exist. In the way they're operating, these resolution criteria are simply not defined because they are defined for linear systems. And by doing these iterative refinements, they leave the linear system. So you cannot compare the result from one to the other. So, I mean, this is if people deny the influence of symmetry. I mean, looks like it makes sense, but the problem now is, for example, you see all these entries on coronavirus spike proteins, and they don't give the supporting evidence in terms of half maps so that you can compare the results independently, or they don't even do free shell correlation curves, and they behave as if it's all known, and it's actually not even. It's really flawed, and the whole idea of some of these the idea people have is like a signal to noise ratio is information, and that is a wrong way of thinking, and that wrong way of thinking has been introduced into our heads in the first year of university. It took me 40 years to understand that, but that itself was wrong. So one needs to really think twice, and this has serious consequences. I mean, like signal to noise ratio, the quality of your X-ray your X-ray machine. So you have you're suspected of COVID-19, and they want to take pictures of your lungs. The machine with which you do that is verified by basis on the quality of the machine is verified by a thing called the detection quantum efficiency. That's based on signal to noise ratio. So that metric is wrong, which they use to prove that the machine is good. So we're losing people, or losing our very machines that we use to diagnose and to image the internal organs. Those machines are not following the right rules because of these problems of in the very definition of signal to noise ratio. And that will take a while for people to accept and to digest. It's it's pretty fundamental. I mean, this is stuff that had been published before I was born by Shannon and other people, yeah. And and it was a different world. It was in the world in which you just had a telephone line or something is installed, yes, and you had and people thought about data differently. There was no how do you call it, wave function ideas behind it. So it's complicated. I think Vanderlei wants to wrap up.
Yeah, also, I guess, considering like this very strong and very precise words, I will start wrapping up. So, Professor Van Heel, with your time, I believe that Professor Vanderlei Souza would like to say some final words. So, Professor?
Thank you very much
Yes.
for inviting me, and thank you very much for yes. I mean, it's difficult to not see the people and not get the feedback, and the time flies. Okay,
it's a different situation for all of us.
It's a different experience. I would much rather be in Rio de Janeiro and have a good time and lecture and go for a beer afterwards.
We'll be looking forward for that.
Okay.
Okay. Yeah. Okay. I think there is a problem with my phone. Well,
we can hear you.
We can hear you.
Yeah. Thanks again, Mary, for this wonderful talk. I would like to see in the future the use of this new approach, comparing the results you have obtained with hemocyanin and etc., using the two approaches, the old one and the new one, to see the big advantages you can get in terms of information. And I hope you can come here personally as soon as the pandemic goes down. We are just established a more strong cooperation between our National Bioimaging Center and CPEM. And this will be very important to increase our cooperation. Bye-bye.
Obrigado, professor.
Nada. Tudo certinho.